So welcome back again in the class of microfilters. I'm your instructor Zubair Akhtar. So in previous classes we have seen like theoretical background of designing a filter and how we can like synthesize a low pass filter, and we have seen in the last class like how these low pass filter can be translated into a band pass filter. So in this class we're going to do our one design example for band pass filter. Okay, so I'm reading the problem for you. So the problem statement says we have to design a band pass filter having a 0.5 dB of equal ripple response. Okay, so by this statement we can say the ripple factor is 0.5 dB. So by making this statement we somehow are aware of the type of the filter. So this filter gonna be Chebyshev filter. Okay, so the statement says we need to design a band pass filter. So the filter type band pass filter with the ripple factor of 0.5 dB, and this filter is Chebyshev filter. Okay, and then they have given the order of the filter as 3. So the order of the filter represented by n, which is 3. They have given us the center frequency is 1 gigahertz. So if we say the frequency in hertz, so 1 gigahertz. The bandwidth is 10%. So they have given the bandwidth is equals to 10%. Okay, and they have also given as the system impedance Z0 as 50 ohm. Okay, so this is the problem statement, and now we need to see how we can design a band pass filter with this kind of a design consideration. So in previous classes what we have seen, if we design a low pass filter, so as the order is given, so I'm just drawing an equivalent circuit for this. Okay, so this is a third order filter. So if we say this is as L1, this is as C2, and this is at L3. So if we design a low pass filter with the same order, say n equals to 3, with a cutoff frequency as similar to this. So here, so sorry, we not to say as a cutoff frequency, it is the center frequency. Okay, so F0. For band pass filter, it is a center frequency, and for low pass filter, it is a cutoff frequency. Okay, so if we design a low pass filter with a cutoff frequency, which is exactly at the center frequency of band pass filter, so we can translate this low pass filter to an equivalent band pass characteristic with the kind of suitable transformation. So we have seen that transformation is somewhat equivalent to, we need to replace the series inductor with a combination of series inductor and a capacitor. Okay, and this parallel capacitor is a combination of parallel inductor and a parallel capacitor. So we have seen this, and similarly the series inductor again gonna be replaced with a series inductor and capacitor. So let's assume this is your L1 dash, this is your C1 dash, this is your L2 dash, this is your C2 dash, L3 dash, and C3 dash. Okay, so the first step is to design a low pass filter with the cutoff frequency is equals to the center frequency given in the band pass filter, and the second step is to convert this low pass filter into an equivalent band pass filter by replacing the series inductor with a series combination of inductor and capacitor, and so on and so forth. We have also seen like how we can calculate these values, and we have obtained these expressions. So let me write these expressions for you. Okay, so for series combinations, L1 dash, this is having a relationship between this element in the low pass filter which is equals to L1 Z0 divided by omega naught into delta. Okay. Now C1 dash can also be calculated with this expression, delta divided by omega naught L into Z0. Okay, this is for the series elements. So L1 having a relationship between L1 dash and C1 dash, so L1 dash and C1 dash can be expressed in terms of the low pass values of the inductor and capacitor. What gonna be this transformation leads to for the parallel element, the C2? So this C2 can be replaced with the parallel combination of L, a capacitor, and inductor. So this transformation will somewhat like L2 dash. Okay, so we have obtained this before, so this gonna be equivalent to Z0 divided by omega naught into C, and the C2 dash is equivalent to C divided by omega naught delta into Z0. Okay, so now we have the information about like how we can calculate all these values for designing a bandpass filter with the help of low pass filter. So let's start with the first, the very basic is to design a low pass filter. So the first step is for calculating these is calculation of G parameter. So for Chebyshev filters, we have seen in previous one example how to calculate the values. However, these values can be directly obtained with the kind of the ripple factor from the tables. So I'm just taking those values directly from the table. So for filter order, say n, which is an odd number, okay, so the first source impedance is given as this, and for filter order to be having an odd number, so G4 gonna be also equal to 1. This is the normalized case. Okay. Now if we talk about the G parameter for Chebyshev filter with this ripple factor, so we can directly take these values. However, you can have the calculations we have discussed before in example. So it comes out to be 1.5963 and G2 is equivalent to 1.0967, and with the symmetry we can have like the G3 is equivalent to G1. Okay. So what these G parameter indicates? So these G parameter indicates like we have a source impedance here, okay, and there is one load impedance. So they are 1 and 1 in normalized case, and this inductor in normalized case is 1.5963, and this is 1.0967, and so on. This is 1.5963. Okay, so we have designed a low pass filter at a cutoff frequency as 1 unity. So now we need to transform this to an equivalent cutoff frequency which is equivalent to 1 gigahertz. Okay, so this is called frequency scaling, and now we have a source impedance as 1 and load impedance as 1, and our system impedance is 50, so we need to do frequency as well as the impedance scaling. So these values L1 and L2 are normalized. However, in this expression we have already considered the frequency and the impedance scaling factors, so we can directly obtain these values from the normalized L1 and the normalized L2 and normalized C2. So for this filter, so we can directly calculate what gonna be L1 dash, okay? So L1 dash is equals to L1 in normalized case. So L1 in normalized case is 1.5963, okay? The system impedance for like as 50 ohm, and then omega naught. So we can have omega naught into delta, okay? So omega naught is given for us, okay? Omega naught is given and delta, okay? So these two things we need to understand by the statement. So delta is defined as divided by omega naught. So omega naught is the center frequency. If we say the bandwidth of the filter is 10%, so this delta comes out to be 0.1, okay? What gonna be omega 0? Omega 0 is 2 pi f0. So 2 pi f0 is 1 into 10 to the power 9, 1 gigahertz, okay? By putting these values, like we have 2 pi into 10 to the power 9, and then we have delta as 0.1. So we can solve this expression, okay, for a series combination here, L1 dash. Similarly, the C1 dash expression is delta, which is 0.1, divided by omega naught. So it's 2 pi into 10 to the power 9. Then again a multiplication by the system impedance. So we can calculate this value from this expression. So this is an inductor replacing a combination of series inductor and capacitor. And now we need to calculate the equivalence of this capacitor with this network. So we need to use these expressions. So L2 dash is delta is 0.1 into 50 divided by omega naught, it's 2 pi into 10 to the power 9, and C is C2 here, okay? So these are C2. So C2 is 1.0967, okay? Similarly for C2 dash, the expression is C2, so 1.0967 divided by omega naught, it's 2 pi 10 to the power 9 multiplied by delta and multiplied by 50, okay? So if we calculate these values, so I'm just writing it down for you. So L1 dash, this is one comes out to be 127 nanohenry, okay? And the C1 dash is comes out to be 0.199 picofarad, okay? And this value is comes out to be L2 dash is 0.725 nanohenry, 725 nanohenry, and C2 dash is, while calculating, is 34.9 picofarad, okay? So now we have like have the equivalence of this element and this element, and due to the symmetry, the equivalence of this to this series combination we can directly predict from these. So L3 dash gonna be equal to L1 dash 127 nanohenry. Similarly, the C3 dash gonna be equals to C1 dash, which is equals to 199 picofarad. So now we have every value and we can design our bandpass filter. So our bandpass filter, the resultant bandpass filter would be like 50 ohm, and then we have an inductor, then we have a capacitor, then again an inductor and a capacitor, okay? Then we have another inductor and a capacitor, and this is terminated at a system impedance of 50 ohm. Okay, so this value is equivalent to this, so 127 nanohenry. Okay, and this capacitor is 199 picofarad. So as this value as 127 nanohenry, and this value is 0.199 picofarad, and for this combination we need to see the values 0.725 nanohenry, and here we have 34.9 picofarad. So you can choose any circuit simulator to calculate. There are a lot of circuit simulator. You can make a circuit, say multisim or some other simulators as well, and you can like simulate this circuit and try to see the transfer function, like how the transfer function of this like network is behaving. So we need to confirm this by seeing the transfer function. It should be something like this, and center frequency around 1 gigahertz. So this is your simulation exercise. You need to design this in any of the simulator and try to see whether this transfer function is giving you a bandpass filter or not. Thank you.